My name is Cameron Phillips. I'm an applications engineer that covers ESD and Surge and also smart power switches. And today I will be showing the ESD and Surge portfolio overview. Today we'll be going over the ESD and Surge training that we have and the associated collateral that we released online, also the ESD portfolio and the collateral associated with that, and the flat clamp portfolio, which is our new Surge devices. It's important to note for ESD devices the difference between DC and transient events. So the DC characteristics for the ESD device are for it to remain invisible on the line. This is where you get the VRWM, which is the reverse standoff voltage, which shows what signals can go through with very low leakage for it, and that will not be affected by the system. Then looking at the breakdown voltage for it, the breakdown voltage is where the diode curve starts to become conductive. This means that after this point, after this voltage point, the diode will start conducting as much current as it is given. So whenever you're choosing ESD diodes, you want to make sure that your signal that you are putting these diodes on is going to be under or at the VRWM and not at the breakdown voltage. Also going into the ESD device, the general characteristics of the ESD devices, we have the unidirectional and bidirectional ESD diodes. And the question that we always get is, when do I use a unidirectional, when do I use a bidirectional? So if you have a unidirectional signal shown here where the signal swings above ground only, you can use a bidirectional diode. However, you're not going to get as good of clamping on the negative side for these events, but it's not going to inhibit your signal at all. However, the better solution would be to have the unidirectional diode instead of the bidirectional, but they still both can work. When you have a bidirectional signal, your signal swings below ground. This means that you have to use a bidirectional ESD diode so it does not affect the operating region of the device. Because if you use a unidirectional diode, you'll be clipping the voltage in the negative direction. Now, this is commonly found more on analog applications such as ADCs and things of that nature, because those devices definitely do swing below ground. On digital outputs, most of the time they swing above ground. So now I want to go over the capacitance and the signal integrity aspect. So this is all feeding into the fact that the ESD diodes are supposed to not affect the system and then are supposed to do their job whenever they have an ESD event. So this goes into the not affecting the system aspect. The capacitance of an ESD, or the junction capacitance of an ESD diode, needs to be within a range to allow the signal to pass through without being clipped, as you can see there. The difference between the two pictures on the top and the one on the right, this one has lower capacitance. It's an HDMI 2.0 signal, and you can see that there's clear differentiation for all the signals. However, whenever there's too much capacitance on the line, those signals get mixed up and you won't be able to tell what's a 1, what's a 0. So we've come up with a general rule of thumb for each of these common interfaces to show the recommended capacitance on that line, and then also our recommended devices for the associated capacitance. So now let's get into the actual doing your job part of the ESD diode. The ESD standard has been defined by IEC 61004-2. This just means that you have a large voltage source that is discharged onto a capacitor and resistor made up here and gives you this current profile that you can see over here on the right. Now, there's different levels to this ESD test, and that's what you'll hear many people talk about whenever they're talking about ESD. I need level 1, I need level 2. But most of the time people are going to say, I need level 4 ESD as a baseline, which level 4 ESD means that it is plus or minus 8 kV contact and plus or minus 15 kV air gap. Now, getting more into the transient nature versus the DC nature, I wanted to point out the big differentiation between the DC spec and the transient spec. The transient spec is made up of different pulses that go onto the line that will then measure the current that's going through the device and the associated voltage that's going through the device. This is important because if you compare the current for this transmission line pulse to the IEC 61004-2 current pulse, you can see that at 16 amps and at 30 nanoseconds, the pulses align. So what this generally tells you is when you look at TLP graphs that all ESD diodes have, you're going to be able to say, okay, at 8 amps of current, the clamping voltage is 10 volts. This means for 4 kV of IEC, the clamping voltage would be around 10 volts. This is more applicable, though, in the 16 amp range, which is the level 4 that we talked about earlier, the 8 kV contact, and that goes up to 14 volts DC. So this is important for systems because all systems or all ICs have a small onboard ESD chip, and this ESD chip is going to protect from HBM, CBM. I'm sure that you've heard of these different small standards. These are more for handling of the device. When we talk about IEC 61004-2, we're talking about a system level standard that is actually discharging a charged conductor onto your device. So the small internal ESD cells that all ICs have is not going to be able to protect for high ESD events that are defined in this standard. So what we do is that we take some of our devices, which, as you can see here, this device breaks at about 9 volts in the positive direction, and in the negative direction breaks about negative 5 volts. So we know now that if we can find an ESD diode that at 3.5 amps has a clamping voltage less than 9 volts, we know that it can protect from the positive ESD strikes. Similarly, in the negative direction, if we can find an ESD diode that has less than negative 5.71 volts for 3.5 amps, we know that for the negative direction, we're going to be able to protect this device. This moves into our whole designing ESD with the system in mind. So if you take the TLP curve for some chip and you say that it breaks at 9 volts and 5 amps, so then you take your ESD diode and you say, all right, well, the ESD diode doesn't break at 9 volts, 11 amps, but that is the point at which it's on the graph. So you can say that for 11 amps going through the ESD diode, there's 9 volts associated with that. So if you add the two currents together, the 5 amps and the 11 amps, you'll get a total system protection level of 16 amps. This means that your ESD diode just has to clamp low enough that you can pass as the system the ESD pulses. Now the trade-off, or now what naturally comes to mind is that, well, what if I just have the ESD device clamp so low that the internal ESD circuit would never turn on? This in theory works, but there is a inversely proportional relationship between capacitance and the clamping voltage, which means that if you're going to have a very low clamping voltage, even at high currents, your capacitance is going to go way up. And it goes back to what we were talking about earlier, the don't affect the system during normal operation. So if you have a higher capacitance and your system can't handle that higher capacitance on the signal lines, then you're going to affect your normal operation and your signals won't pass uninhibited. Now, talking about surge, I wanted to basically contrast the ESD pulse and the surge pulse. The ESD pulse is a 200 nanosecond pulse, while the surge pulse is a multiple microsecond. This means for ESD events, the pulse, it looks like it's much higher, but the total energy that is carried within the pulse over time is going to be favoring the surge pulse by a lot. So the DC aspects of surge diodes still hold true with ESD diodes. So we're talking about the breakdown voltage, the working voltage, the capacitance, all of that still has to do with surge diodes. However, what they're going to be dissipating is a much higher energy pulse. And to differentiate between what needs surge and what needs ESD, it's very dependent on the market. So for the personal electronics section, most of the time they just need ESD. For building automation, enterprise, and comms, however, they need ESD and surge. And so you just have to know, based on your end equipment, what is the environment that it's going to be exposed to, and therefore what device do I need to protect against it. So I just wanted to leave with this little tidbit to point you to some excellent collateral that we have for ESD and Surge that just goes over the training in very small bite-sized portions. They're about 3 minutes long each, and they do a great job of detailing what exactly the ESD needs and what exactly the Surge needs, and some of their applications and where you'll find the different parts of them. We also have this white paper that goes through our flat clamp technology, which is our new TVS devices that are different than older generic TVS devices. And so this actually walks through how we're able to get that technology in the differentiations between this technology and the old technology. And I'll get into that in the third section. But I just wanted to very much highlight that these training videos are excellent and they're very easy to digest. Switching gears, I wanted to get more into our ESD and Surge portfolios. So we separate ourselves with our high performance ESD diodes and our flat clamp surge protection. So those are the two different parts of our devices. And so first, let's get into our ESD portfolio. So our ESD portfolio, we've released many parts that cover the most of the entire market, such as some of our new parts, which is this ESD 321 and ESD 351, which has relatively low capacitance. It can work on the USB 2.0 lines, 30 kV protection, and it has relatively decent surge for these one-channel parts here. Also, if you move to 2-channel and 4-channel, we have these new parts for our high surge, high discrete surge protection, which goes up to 12 amps to 25 amps of surge, that have relatively low capacitance for them and can work on most of the Ethernet, general purpose, some USB applications, things of that nature. And they're very good for high performance but still discrete. And we'll differentiate between these discrete diodes versus our flat clamp portfolio later on. Also, just some other things to point out: the stars by them are hero products that we're doing great with, that customers really enjoy, and that have been useful for all of their parts. So each of them have a associated package next to it. So you can see that we have devices in the 0201 package, 0402 package. We have devices in these USON packages, which is industry standard. TI calls it DQA. And then we have the SOT packages too, that are the standard SOT 323. I mean the SOT 6 pin package, and so we have several that are also auto qualified too, which you see with the little cars next to them to show off our auto portfolio. Highlighting more deep down, we have the high-speed devices that we release. So a lot of these systems with the high-speed signals have multiple signal channels that the signal is spread out on, and so they really enjoy these 4-channel devices in this nice flow-through package that allows not very much signal integrity loss. So the differentiation between these is the 4E05E06 is a 5-volt device. The 4E02B04 is an ultra-low capacitance device. The ESD224 isn't exactly flow-through because it does have a series element internal to it, but it has the lowest clamping performance of our entire high-speed devices, but can still handle HDMI 2.0. And then our ESD204 is our highest performance as far as 30 kV and the highest surge level of 5.5 amps. Next, I wanted to go through our 30 kV ESD portfolio. These are just parts that are differentiated because of their high performance. And so the first several of these, you'll see the first 4 of these are single channel devices that we have that are all in this 0402 package, and they each serve a different need in there. And again, if you go back to the videos, each of these specifications is explained in more detail in those videos and in the training beforehand. Then we move on to our 4-channel and our 2 to 4-channel devices. These are our high surge discrete devices and our high surge high speed device here. And it just shows off our breadth of portfolio for the 30 kV ESD devices. Hammering it back home, these are great parts that we have. This ESD204 is a very good part with 30 kV ESD contact and air gap and 5.5 amps with very low capacitance for having that much protection. This can be used on HDMI, USB, Ethernet, all sorts of standard because it has such a low capacitance of about half of a picofarad. Also diving into the new surge devices, the discrete surge devices that we released, we have these 12 amp surge devices that clamp at 5.8 volts and these 25 amp surge devices that clamp at 5.5 volts, which is extremely low for them, for these devices, and can protect almost any downstream device like this USB transceiver, the Ethernet PHY, as long as they can support the capacitance for it. So for USB 2.0, the 2.3 capacitance for the 302 device is acceptable for USB 2.0, and the 312 device, the 4.5 picofarad, is acceptable for the gigabit Ethernet application because the gigabit is split up between the pairs of wires. Again, these are our 4-channel devices. They're the exact same as our 2-channel. They just have more channels. And they have the same specs of 5.8 volts and 5.5 volts for the different surge levels, and the same capacitance, and these devices are 3.3 volt devices. So just wanted to leave with this little tidbit of we have these great pieces of collateral. The system level ESD protection guide goes through some very standard interfaces that we have that will explain what the interface requires, why it requires that, and what are our best parts to promote in that space. Then we also have our ESD by interface guide, which if you don't want to know all the background behind it for the system level guide, you can jump to the ESD by interface guide, and that will just show you immediately what part that you need for um, a given interface. We also have this choosing simulation models for ESD devices document that goes through the pros and cons of each of the different type of simulation models that you can have, and basically ends up with the idea that if you want to simulate for ESD protection levels, then using the TLP graph is going to be your best case scenario because it's the quickest and it's the easiest to tell what is going to protect. Switching gears now into our flat clamp TVS diodes portfolio, I just wanted to point out that these are differentiated from typical TVS diodes based on the size of them, based on their clamping voltage during surge events, how flat it is, and we'll get into that in the next slide. We also have significantly lower leakage than most of the TVS diodes out there, and the temperature derating is leaps and bounds above the competition with these SMA SMB diodes. So going into the clamping performance, we see for a typical TVS diode, such as this SMA device over here, the clamping voltage, even though it's a 33 volt device for their working voltage, and the breakdown is 37 volts, whenever you actually have the surge pulse, the clamping voltage goes all the way up to 46 volts. This means that your whole system has to now be able to withstand higher than 46 volts in order for the system to survive a surge event. Contrast that with our TVS 3300, which even though the breakdown is 35 volts, the clamping voltage for it only goes up to 36.8 volts, or I believe a max of 40 volts. This means that your entire system can now be tolerant to 40 volt lines instead of, for the SMA device, has to be tolerant to 50 volts. And this can be huge savings for a lot of different ICs that aren't rated as high. One of a huge advantage that we have are the size difference in the packages. So this is a visual representation, and I'll have a couple more visual representations after this that shows you basically the difference between the SMA package and our flat clamp device with a 4mm package, and then even our TVS 3300, which has 1.2 millimeters in the WCSP package. So we are showing here that for the same, if not better performance in our devices, you get a huge reduction in the size. And that's especially true here, where we can actually show the difference, where we can fit two of our TVS 3300 diodes in the size of an SMA device. And this is showing right here the WCSP package, but it's just a good visual representation of how much space savings there actually is. This means that when you have a smaller device, you can put it closer to the connector. You'll take up less space, obviously. And having it closer to the connector means that you're not going to have as much EMI whenever you have any of these sort of transient events, because it's going to be able to shunt whenever it's closer to the connector. It's going to be able to shunt the current. So going into our portfolio, we have our unidirectional flat clamp devices, which have voltage ranges from 33 volts down to 5 volts with different increments. And it also shows you the maximum clamping voltage that each of these have for their associated device. And it just and this is at their highest level, most of them around 35 amps. Some of the lower voltage are at higher current levels, and you can see their data sheets whenever you go to them. The leakage also, as I pointed out earlier, is much lower than competition. Competition is around a microamp maximum leakage. So we wanted to really point out that we can spec down the leakage down to the sub-nanoamp region even, and the single to double-digit nanoamp region for most of these devices, even at 85 degrees Celsius. Again, this shows the 2x2 package versus the SMA SMB packages, and just showing that it's a greater than 70% area reduction. These are our bidirectional devices, which are 3x3mm, so a little bit bigger than our unidirectional devices, but a still 50% reduction over the SMA SMB packages, and this just shows the clamping voltage as well associated with them that is still extremely tight relative to the SMA SMB bidirectional devices for the 1 kV 42 ohm surge immunity, which is talked about in the surge protection videos that I alluded to earlier, and we'll show a little bit of them later. They have very many applications, and a common question we get is, well, why do I use bidirectional or unidirectional on these? And the bidirectional version are good for applications where there's reverse wiring that can happen. Some people call it reverse polarity, to make sure that your TVS diode doesn't break down during that event and then cause it to break. So it's a way to have the nice, very flat clamping that we have in our devices, but still make it applicable for a wider range of applications. So the last thing I wanted to leave with is the collateral that we have associated with it. We have this EVM, which is putting our device in the industry standard SMA SMB footprints and showing everyone that you can take this device, put it into your system, test it out where your TVS diode was, and you can see the benefits for yourself in the system with it in there. And then the next generation of projects, you can then build a board around this device and give you the space savings that is a big selling factor for this device. And so we have these little coupon boards that are available online, and it gives you the entire portfolio of our flat clamp devices and several samples of each of them. Also talking about the demystifying the surge protection, as was the title of the videos, we have a white paper associated with it that shows the where surge is, how different equipments are affected, and different things of why it's needed for the system. And then finally, we have this selection guide for surge diodes, which is just what are the key specs for surge diodes that I need to look at whenever I'm selecting a surge diode for my system.